Hello, I'm Nitisha Jain, a PhD student at the Hasso-Plattner Institute in Germany. I'm talking about our recent work on knowledge graph representation with embeddings. Knowledge graph embeddings are aimed at embedding the components of a knowledge graph, that is, the entities and the relations, into continuous vector spaces. This allows for easy manipulation of the data while preserving the inherent structure of the knowledge graph. This way, we can capture the interactions between the different entities of the knowledge graph in the continuous vector space. In the recent years, many different embedding models have been proposed. They have become quite popular, with several new models being proposed every year. Some of the most prominent ones are Trans-E, Rescal, Disk-Mult, Complex, Conv, and many others. Due to their popularity, the applications of these embeddings have become widespread. Apart from the link prediction task for knowledge graph completion, they're also being used for several other semantic tasks, such as entity and relation similarity, conceptual clustering, and so on. All these use cases attempt to leverage the semantic knowledge which is included in the embeddings. However, the scalability or the consistency of these approaches has not been measured across different knowledge graph datasets as well as different entities in the same dataset. This was the focus of our recent work titled "Do Embeddings Actually Capture Knowledge Graph Semantics?", which was presented earlier this year at the Extended Semantic Web Conference. In this work, we are trying to see whether the premise that vectors of entities and relations reflect their latent semantics actually holds or not. The expectation is that similar entities such as E1, E2, E3 in the knowledge graph, when mapped to their continuous vector spaces, should also be similar. So the expectation is that entity similarity is reflected by the vectors. So all the painters, all the politicians, and all the academics should be closely clustered in the vector space. However, in reality, fine-grained semantics are not really reflected, and all these entities occur together clustered in the continuous vector space. So the objective of our work was to do a comprehensive analysis of the characteristics of the latent vectors from the embeddings, quantitatively measure their ability for semantic representation, and explore the reasons of the shortcomings that we saw. Now, how do we go about measuring this semantic expressiveness? The idea was to use entity classification and entity clustering to identify this. These two tasks are suitable for semantic analysis since they are simple and they can identify the salient features of the embeddings if any present. So in entity classification, all the entities belonging to the same type should be classified to their respective types, whereas in entity clustering, the different clusters should ideally reflect different class types of the entities. The way we prepared the dataset for these experiments is that we created a tree of the entities according to their semantic types. So for example, person, organization, body of water, and product were the level 1 entity types. Then going down further, we have a person could be a scientist, artist, office holder, musician, and so on. And similarly, we constructed an ontology tree for different entities. These subtrees were explored manually, and the most frequent classes were chosen. And then the experiments for classification and clustering were performed at the same level of granularity for fair comparison. For the experiments, we chose various different embedding models implemented in the libkga library. As a non-embedding baseline, we chose the ST-type entity typing technique, which is a heuristics-based technique relying only on statistical distribution of the entity links. This technique is robust to noisy facts and agnostic to any existing type information. Various different algorithms for classification and clustering were explored. Here I'm talking only about classification, and the clustering experiment details can be found in our paper. The results from our classification experiments on the Yago dataset in terms of the F1 measure show that while the embedding techniques perform pretty well at level 1, that is at a higher level of granularity of entity types, their performance rapidly decreases when we go to level 2 and level 3, that is fine-grained entity typing. This is observed for all different embedding models as well as all different classifying algorithms. We can see from these results that SD type, which is a non-embedding technique, can already be on par with the embedding performance itself. Now we want to see why is this happening. So a deep dive analysis is needed to understand why semantic expressiveness is so low for embeddings. This is due to the fact that real-world entities frequently belong to more than one semantic type or class. For example, a person could be an actor, businessman, and a politician all at the same time. In this way, most of the relations that are associated with these entities are neither unique nor indicative of any particular class type. For example, relations such as born in, has spouse, is citizen of, do not belay any information about the occupation or the type of this particular entity. So while the expectation is that entity similarity will be reflected by the vectors, in reality, all these entities seem pretty similar in the embedding space and are all placed together. So the major insights from this work was that while it is assumed embeddings represent the semantics of the knowledge graph components well, we found that semantic soundness is actually restricted to very few entities at a higher level. This is highly dependent on the dataset characteristics, and even simple heuristics-based approach can already derive the semantics directly from the knowledge graph triples without any additional information or embedding needed. So the idea is that there is a need for wider analysis and proper inspection of the advantages as well as weaknesses of embeddings. These embeddings, while they perform well for link prediction, but they cannot be generalized for more semantic tasks, and this deserves more attention. And ontology and reasoning can help with improving the semantics of the embeddings. This was addressed in our recent work on improving knowledge graph embeddings with ontological reasoning. This work was done in collaboration with the Bosch Center for AI in Germany. In this work, we see that despite having good link prediction performance, many knowledge graph embeddings may predict semantically incorrect triples. This is because these embeddings are being trained on existing knowledge graph facts, and ontological knowledge is not taken into account during the training of the embeddings. We propose that intelligent training process is needed to avoid nonsensical or undesirable predictions from the embeddings. Now let's have a look at the way knowledge graph embeddings are trained. These are trained by the generation of negative samples for scoring and ranking. So a knowledge graph embedding model is trained to rank positive triples higher than the negative ones. In this example, we can see Mike works at Bosch as a knowledge graph triple, and various negative samples are being generated for these triples for providing the embedding model during its training. The idea is that when fact prediction is performed with the model, the actually correct triple, which is Mike works at Bosch, will be ranked higher than the incorrect ones. Negative sample generation for knowledge graph embedding training is generally considered to be a challenging task due to the open world assumption. Previously, the negative sampling techniques employed have been random or local closed world assumption based. However, these techniques have many shortcomings. These techniques might lead to false positive, which is the case where a negative sample is actually true in reality. This will also not consider the difficult cases, and similar sampling is being done for all the triples of the knowledge graph. And of course, there is no consideration of the ontological information, and therefore the resulting predictions might be inconsistent with respect to the ontology. We have proposed in this paper a new sampling technique, a technique called Reason KGE, which is ontology-driven and dynamically generates negative sampling during the knowledge graph embedding training. The motivation behind the Reason KGE technique is that when a knowledge graph is embedded to its vector space, we'll have a look at the predictions being made by the resulting embedding model. When a bad prediction is being made, we want to identify it and use it as a negative sample during the next phase of the training. So with the goal being increasing the prediction accuracy of the embedding model, we'd automatically want to detect the inconsistent predictions and then use them as feedback to the training process. This is done with the help of ontology reasoning and a sampling technique. So while the standard embedding methods look like this, our Reason KGE method is adding a few components on top of this pipeline. First of all, we're using the ontology for doing consistency checking of the predicted triples. And once the inconsistent predicted triples are identified, they are fed to a generalization module and then fed as negative samples to the next iteration. The results with link prediction are quite promising. These results show that Reason KGE performs very well is compared to default training as well as static sampling method. In almost all the cases for both embedding models and knowledge graph datasets, we basically improve the link prediction performance. Also, in terms of the ratio of inconsistent prediction, we see that recent KGE leads to better and more consistent prediction. Lower number here mean better performance because we have less inconsistencies in the top 1 or the top K predictions. So overall, for both subject as well as object prediction, recent KGE performs quite well. For further details, please check out our recent papers. And for any questions and further comments, please contact us via email.